Hello everyone, today we will be presenting our course project for ECE 591, which is on time series forecasting. The title of our project is Ensembled Time Series, Stock Forecasting using GluonTs. About the aim of the project, some of the related work, our dataset, methodology, experiments, results, and what we learned, and future work. So let's talk about a few key points of this project. Time series modeling is making predictions about events in the future. It is essential for business, anomaly detection, and medical domains. Model ensembling is combining two or more related but different models and then synthesizing the results into a single score to aid generalization. Many methods have been implemented, such as statistical models like ARIMA, machine learning models, and deep learning models. GluonTs is a platform which has deep learning models for time series forecasting. The goal of this project to achieve high-level accuracy for time series forecasting by leveraging Wharton Research Data Services repository. The results will be compared with the plots and mean square error. Over the past several decades, time series forecasting solutions have undergone a progression from traditional statistical methods such as ARIMA and machine learning techniques like XGBoost to deep learning-based solutions, for example CNN models, LSTM, or RNN. Autoregressive integrated moving average short as ARIMA models use differencing to convert a non-stationary time series into a stationary one, and then predict future values from historical data. These models use autocorrelations and moving averages over residual errors in the data to forecast future values. XGBoost, which stands for Extreme Gradient Boosting, is Scalable Distributed Gradient Boosted Decision Tree (GBDT) machine learning library. Neural network is a layered structure of connected neurons inspired by biological neural networks. The neurons of RNN have a cell state memory, and input is processed according to this internal state, which is achieved with the help of loops within the neural network. There are recurring model of layers in RNNs that allow them to retain information. Long short-term memory networks, or LSTMs for short, can be applied to time series forecasting. It is a special kind of recurrent neural network that is capable of learning long-term dependencies in data.
This data is provided to us by the Wharton Research Data Service repository, which is a non-public online data source for a variety of topics. The data begins in 1958 and goes on until March 2022. We use a 75-25% testing training split. We're predicting the average daily close price of stock. So just for a note, that's not the same as what you see as the normal price for each day of the S&P 500, which is based on its market cap. We're predicting the average daily close price, which is a bit different. And we're using just a date field here to predict that, which is no explicit feature engineering is necessary with these deep learning models, unlike machine learning. It was actually a massive data set with think of all of these stocks. I've been in the S&P 500 since 1958, and so we really did fight some issues of size. Building off those issues of size, our data cleaning was actually a little bit more involved than I think we thought it would be, especially considering the reputation of the repository. There was a lot of NAs, so you can actually see here in this graph, these little slits are actually where we're missing data. So what we did is we would backfill all these with the previous day. So if we're missing some for here, we use the previous day and just assume there was no drop. So we padded by day. GluonTs also has a special format for its data frames, so we had to work with that, which is a little bit of a bugger getting that set up. And then over this, we actually have non-constant variance, which is actually an assumption you need constant variance for a time series regression model, whichever. So we address that with a logarithmic transformation. Okay, cool. So with all that in mind, let's get into our approaches. Okay, so the real bulk of this project is going to be done using GluonTs. So GluonTs is really arguably the best method right now for deep learning models, specifically for time series modeling. It's developed by Amazon in 2019. And what it really does is it's a wrapper that takes in a whole bunch of different models and has other methods and objects built in to allow for a full development of time series modeling techniques. It really leverages a great computational format that allows it to be incredibly powerful. But the flip side of this is that it's not always the easiest getting a hang of. And like I kind of mentioned earlier, like every data set has to be the specific type, and everything has to be formatted exactly the way that GluonTs likes it. So it took a little bit of time getting comfortable, understanding what it needs, what it can't have, and then finding some parameters really played well.
Let's talk about our first model, Deep AR model. Deep AR is an autoregressive recurrent neural network that leverages covariate target values at previous time steps and network outputs to provide high level of accuracy. Deep AR is a multi-layer RNN architecture which incorporates a negative binomial likelihood for count data. You can see a partially unrolled RNN with an output layer and multiple hidden layers like Deep AR uses. This model is implemented to Google Colab using these parameters: context length of 6, prediction length of 10, learning rate of e to the minus 3, with 50 epochs and 20 batches per epoch. Our second model is called Simple Feedforward. Simple feedforward is, as described, a simple, multi-layer perceptron that predicts future time steps with previous ones. For this study, the simple feedforward has 10 hidden dimensions. To implement this model, we use hyperparameters of content length of 210 days, prediction length of 10, a learning rate of e to the minus 5, with 50 epochs and 20 batches per epoch. As we mentioned before, the ensembling is done by combining two or more models. The models Deep AR and Simple Feedforward are used to implement this model. Weighted average is implemented by trial and error method, using the fact that Deep AR performed better than the Simple Feedforward. The weight for Simple Feedforward is chosen to be 0.2, and the weight for the Deep AR is chosen to be 0.8. Hyperparameters copied exactly given before slides. We were able to do this since both models' outputs were class sample forecast. As can be seen from the figure, outputs are stored in samples of the forecast. So what we did was to reach the samples and take the weighted averages. Many other methods has been tested, but only this way worked because GluonTs requires a specific data types.
Okay, next model discussion is the temporal fusion transformer. So the TFT is a novel attention-based architecture that uses high-performance multi-horizon forecasting and interpretable insights into temporal dynamics, which is taken directly from the paper. The TFT has 32, our TFT, pardon me, has 32 hidden dimensions with 4 heads and a dropper rate of 0.1. Whereas the other hyperparameters is a context length of 6 again. As always, we're predicting 10 days in the future. Has a learning rate of 1 to the e to the minus 3. The weight decay was actually a little bit larger than standard. We went with a 1e4. And then, as always, we're training 50 epochs with 20 batches per epoch. Okay. Our last one here is the NBeats ensemble. The NBeats is probably the trickiest one to explain of them, but NBeats itself is a deep neural architecture based on backwards and forward residual links and a very deep stack of fully connected layers. Okay. So the big hyperparameters for the NBeats are the meta context length, meta loss function, and the meta bagging size. Okay. So how these work, and this is specific to the ensemble model, where the context length is, so it's a list of context lengths you want to loop over. So for ours, we actually chose a context length of 3, 6, and 10. So it's going to create models for a 3-day context length, a 6-day context length, and a 10-day context length. And then it will take a list of loss functions. So for ours, we only fed SMAPE, which actually looking back after we were kind of talking about our performance is maybe a mistake because it's actually percent error, so this isn't going to penalize extreme outliers as much as we wanted to. But oh well, it's what we went with. And then finally, the bagging size. So it's the number of models that share the parameter combination of context length and bagging size. So basically, it's like we're going to create 6 models with a 3-day context length and a SMAPE loss function. And we're going to create um, 6 more models with a 6-day context length and a SMAPE loss function. And then finally, we'll have 6 models with a 10-day context length and a SMAPE loss function, right? So it's just the amount of times you're going to randomize it. So overall, this creates an 18 MBEATS model ensemble, and our learning rate went to 1e to the minus 3.
So let's talk about our results. These are our result plots for simple feed-forward, deep AR, and ensemble model. We should make a note that we spent many hours to implement the best model with changing the parameters. With the plots, we can conclude that simple feed-forward has a greater error range, such that the data before prediction looks more linear. However, it is due to the 90% prediction interval is much higher than the other 2 models. Deep AI performs better than simple feed-forward and follows the first few days perfectly. The ensemble model worked better than 2 models. The prediction is closer to the ground truth, and verify our prediction and intention of creating a better model using ensembling.
Okay, so now we'll look at the TFT and the MBS ensemble. Starting with the TFT, also know that the output of this model is a little different, so we had to edit our plotting style. The MBS actually did really well with the upper bound of its forecast, having 2 points of contact with the actual, but overall being a little bit on the low side. Meanwhile, the MBS ensemble missed by a little bit more, as you'll see in the validation metrics coming up soon. But it kind of stayed below the line. We couldn't get any direct hits there where our prediction crossed were actual. But overall, both of these were predicting relatively well, with the TFT definitely performing better than the MBs.
You can see our mean square error values for each implementation. The worst model according to the mean square error is simple feed-forward, and the best model is the self-ensemble model. We believe that the results we got should have worked better for TFT and NBITS, but it ended up lower than DPR because of the dataset that we are using.
Further work can be done in this model to make it more predictive and accurate. A few examples include callback functions, which could be implemented to the trainer to provide a better convergence to the global minimum. Optuna is a well-known library that works well with GluonTs for hyperparameter tuning. Training testing splits can be manipulated to include more training data closer to the prediction length. Multiple time series could be used, which creates an individual prediction for each stock in the model, as opposed to averaging all prices together. The model time package in R is a great implementation for GluonTs that can be used to ensemble machine learning and statistical methods and is very accurate. Finally, we could have some more computational power with GPU and RAM, specifically GPU training and RAM capacity for ensemble models. And then it would be good to have some domain expert input from someone from the financial world. Okay, in conclusion, time series modeling is an area with high value because many response variables can be modeled according to their relationship with time. GluonTs is a cutting edge library for deep learning models. We tried to predict the daily close price of stocks in the S&P 500. We did a whole bunch of data cleaning to get into a format that played nice. We used DeepAR, Simple Feed Forward, MBEATS, and TFT to assess the accuracy of this model. And then the DeepAR, Simple Feed Forward Ensemble was the best in performing model with a validation mean squared error loss of 2.812e from -4. And in future work can incorporate better hyperparameter tuning, superior computational power, and more sophisticated ensembling. Thank you. Okay, so now we're just going to go over a little bit of a demo of our project. So the first thing we had to do was we had to do an install of GluonTs and MXNet. And then we had to load in a whole bunch of libraries here. Really nothing that special here. Biggest thing is just the pandas dataset function. This is one. It creates a specific object for GluonTs. It's not quite. It's a pandas-like, but it's not quite pandas. The evaluator, how we make our predictions. For this, we're looking at a simple feed-forward estimator and a trainer. Yeah, that's kind of about it. We had to do some Google Colab stuff for accessing local data. We select our columns that we want, where we're only looking at the log data close. Here's where we do our NA filling, where we forward fill. So we move them forward, right? Here we're doing our train testing split. So this is at 75-25%. Here's where we use the pandas dataset function, which creates that nice object. Okay, and then here is the model itself. So the simple feed forward is relatively simple and simple. So we're doing the 10-day prediction length. This one uses the context length of 210 days. Here we're using the CPU with 50 epochs. Pretty small learning rate here. And then 20 batches per epoch. We run our predictor function, which gives us all our nice training. Here we're just calculating our predictions. And then eventually we declare this function, which GluonTs has in their documentation, plot probabilistic forecasts. Where again, you can see this one looks really good, but again, like one of the reasons is the 9% prediction intervals are really high, going from 5.5 down to about 3. Here, I can't see exactly where it cuts off, somewhere about here, which makes the line look really flat. Yeah, I'll show you a comparison in a minute here. Yeah, then we can go into our other sections here, where this is where we get all of our validation metrics here. Yeah, moving on. So most of the script actually stays almost the same. Where it changes for each model is where you look at the model. Looking at TFT again, we've just kind of spoke about this, but it has the 6-day context length, epochs, learning rate, batches, weight decay. This is another hyperparameter for where, anyway, it's not important to our context. But we have 32 hidden dimensions, 4 heads, and a 0.1 dropout rate. Yeah, and here, like I kind of said earlier, but you can see this, like the intervals here from 4.84 to 4.72, where the simple feed forward had those massive intervals from 5.5 to 3, right? So you can just see why it's funny how like the plot looks so differently, but what it really is just how wide I think it can predict in. Yeah, we have our validation metrics. We'll go over our DPAR. We have some nice intersections there, something we love to see crossing through the actuals. Yeah, looking at the model itself, again, this one's actually very simple too, with a 6-day context length and a very standard 0.001 learning rate. Yeah, we'll go to our NBeats ensemble next. Definitely quite a few models trained on this one. You can kind of see, like, since we're doing 50 epochs and 20 batches per epoch, we're training 18 models. This one definitely had a fair share of its fair share of training. I'm not going to go make you see all of them because I think you get it. But sorry, I need to get you the model. There we go. Yeah, so here's where we have our bagging size. We have our context length. We have our loss function. So these are the hyperparameters that create the number of models created for the ensemble estimator. Yeah, and then as far as the NBeats itself, 50 epochs, 1E minus 3 learning rate, and 20 batches per epoch, pretty standard stuff. Moving down the plot, yeah, again, it's spat out a little bit differently. Don't get the same nice confidence intervals, but yeah, you see this one's 484 to 472, so not quite as narrow as the TFT, and this one's a little bit under. Finally, we'll go with the ensemble. So this is the DPAR and the simple feed forward ensemble. So we here we train the simple feed forward, same metrics as before. Then, sorry, I missed it. Where we, yeah, here we train the DPAR. And then we go down. We get our nice little bit of averaging here, where we take 80%, 20% of our forecast samples for each version and combine them together, which gives us our 80-20 split. And then we can re-put this back in our plot function. We got really nice prediction here, a little bit bigger on the confidence intervals, probably coming from the simple feed forward, but nice intersections from this model, showing that it did a really good job. Yeah, so that's kind of basic gist of how it works. In the future, maybe a GitHub repository would have been really nice, and just a little bit better technical work. Anyway, but that's how it goes.
These are our references. Thank you for listening.